This example is pretty similar to the last one, with one key difference. We're asked to put the quadratic function in vertex form. This should say form, and sketch a graph of the function. So we want to go from this general form here to a vertex form. We would like to make this look like this. Okay. So let me show you how we are going to accomplish that. We are going to have to complete the square. And we have seen completing the square already earlier in this course and earlier videos. But let's show how to do that with an actual function. So first thing I'm going to do, and it's not always the first thing that I do, I only do it if necessary. If there's a common factor amongst the x's, I take it out. So it looks like this. Okay. Notice it's all the same terms. It's 2x squared plus 4x. The minus 1 is still there. I just took the 2 out of the 2x terms. Okay. Left a little spot here to complete the square. Now when we complete the square, we add half of this number. So half of 2 is 1. And we square it. Now let's go ahead and write the square. So I'm going to add 1 squared. Now since I'm only working on this side of the equation, if I add 1 squared, I have to undo that. I'm going to take that away as well. And here's the tricky part. I didn't just add 1 squared. I added 2 times 1 squared. So I'm going to take away 2 times 1 squared. As I want this to remain completely balanced. Okay, so this then becomes f of x equals 2 times, let's just write it, I'll do it in a couple steps here, x squared plus 2x plus 1. This is going to become minus 1. This term becomes minus 2. So we get 2 times, what I'm going to do is factor this. This is a perfect square trinomial. Factors x plus 1 squared. These add to minus 3. Okay, if you look at this and compare to this, they look the same now. They look right. So we've got a vertex point at -1, -3. We do have this stretch factor of 2. So instead of doing 1, 2, 4, 3, 9, plotting those points, the vertical distances of 1, 4, 9, the vertical square distances have to double, stretching them times 2. So 1 actually goes to 2 up. 2, instead of going 4, goes 8 up. And out here, 1 goes to 2, 2 goes to 8. If I go 3 from the vertex, it would count out to 18, and that goes off the graph. So these 5 points are going to be enough. Looks about like that. Finally, let's do a little vertical freefall motion problems. This is something that we've seen before. We've actually described it as a position model before. It looks like this. We actually described it a little more specifically. Instead of -1/2 gt squared, g is the acceleration due to gravity constant, and we had said that g can be 32 feet per second squared, or g can be 9.8 meters per second squared. Generally our text uses feet, so if we put 32 in for g, we'd have -16 t squared plus v naught t plus S naught. That's how it was presented earlier in the course, where V naught stands for the initial velocity, S naught stands for the initial position, or the initial height. The Sandusky Little League uses a baseball throwing machine to help train 10-year-olds to catch high pop-ups. It throws the baseball straight up with an initial velocity of 48 feet per second from a height of 3.5 feet. Find an equation that models the height of the ball t seconds after it is thrown. So it's in feet, so we're going to use the negative 16 one. So we got S of t equals negative 16 t squared plus the V naught is 48, that's the initial velocity, t, plus from a height of 3.5 feet. There's our position model. Now part B says what is the maximum height of the baseball will reach and how many seconds will it take to reach that height. So for part B, let me just kind of model this graphically so we can physically kind of interpret this. We've got a baseball, starts at 3.5 feet, travels up, and then back down, eventually lands on the ground. The question is, what's the maximum height and when did it get there? Okay, so what's the time and the S, the height of the ball at that point? Well, if you look at that, that's the vertex point. So we need the vertex, is basically it. If you recall, we had a way to find the vertex. We found the x value by doing negative b divided by 2a. So in this particular equation, it's going to be negative 48 divided by 2 times negative 16. That is reduces down to 3/2, or 1.5. So it reaches the maximum height after 1.5 seconds. Now, what is the maximum height? So how do we find that value? Well, we take that 1.5 and we simply just put it in for the t. Okay, and we work that out. I'm going to just work this out on the calculator off screen. So don't think I'm doing this in my head. And I get 39.5. Okay, so we can say at 1.5 seconds the ball is 39.5 feet in the air, and we can say, since that's the vertex point, that that's the maximum height that the ball reaches.